Welcome to this video on parallelization. So in this video we will talk about how you can use parallelization to speed up your code. I'm importing sort of standard stuff, and then I'm inputting joblib, which is a way to do parallelization in Python, and I'm also importing number, which can also be used for doing some parallelization. And then I will be using quant econ, which you might need to install, which is sort of a package which also have some functions which I will be using together with number. I'm also importing psutil, which sort of can count how many CPUs I have on my computer. I have 8 CPUs on this computer, and here just makes a list of when I will do computation. I will do it with either 8, 1, 2, or 4 CPUs. But let's have a simple example. Let us consider a case where we need to solve the following optimization problem. So this is that we have some solver. It takes in alpha, beta, and gamma. There's an objective function which looks like this. And then we want to minimize this objective function. We guess on 0, 0, 0, and we use the nil-the-mean optimizer to do this. So this is just some example. And let's say we want to do this 4,000 times for random values of alpha, beta, and gamma. So then we can set up a serial solver, which simply takes our results and by solving each of the cases for all the alphas in the lists here. And sort of if we do that on my computer, this takes about 32 seconds to do. So this is a rather slow thing. Now we might say, okay, these are completely separate problems, right? So we could solve them in parallel. We don't need to have solved the first one to solve the next one. So we can just do it at the same time. So we can use joblib for doing this. So joblib can be used to run Python code in parallel. Two important functions from joblib is the joblib.delayed, which takes in a function and the arguments to the function, and then joblib parallel, which takes in a number of jobs, how many CPUs are you using, and what tasks will you be executing. So here I have a parallel solver for joblib. It still puts in the alphas, betas, and gammas, and it puts in how many jobs, how many CPUs I'm using. Then it creates some tasks. That's a generator, where each sort of task that will be generated is from this delayed. So it's the delayed application of the solver on these inputs, and it's the same inputs as before. And then the results are gathered by running joblib parallel with the number of jobs you want on these tasks. And then I just take out the X results here. If I run this for each number of CPUs I have, then if I use 8 CPUs, then I'm cutting the more or less in half. I'm down to 16 seconds compared to the 31 seconds with 1. And actually the fastest thing here is it's actually best to use 4 CPUs here. And that's sort of something you will sometimes experience in parallelizing, that you should guess that using more CPUs should make it sort of as much better as your number of CPUs you're using, but there is various sort of drawbacks of doing parallelization. First of all, the CPUs might have some things that overlap, but it cannot really do it in parallel. When you do this sort of spreading out of the task to the different CPUs, there is some cost because the functions are serialized and copied to each of these processes. So it's sort of a bit unsure about how much speed up you get. It's always better when sort of the inner function here is something that's very computationally heavy, and you can sort of give a lot of tasks to each thread. Then it's the best. But this is speeding up somewhat. Sometimes you can get better results than this. You can also look here for more on joblib, and there are some examples of how it can be used in more general. So this is sort of the go-to thing for general parallelization in Python. You can also use number, where here I will use from quant econ the nil-the-mean solver from quant econ, which is something that can be used inside number. So here I have my solver in number. It's the same objective function, and now I'm using the nil-the-mean as before with the same initial guess. I can use a serial version of that, where I loop through my alphas, betas, and gammas, and I do my solving with this solver, and this is also a JDET function. And you sort of see that this takes a lot of time the first time it's run, because it needs to analyze this code, but the second time it's run, it's only 4 seconds. So that's considerably faster. Number also allowed for a parallel version of this, where I said parallel equal true. And then in this loop here, I'm doing this loop in parallel over the ends. And I get a slight speed up here, but it's not that much. And sometimes Python, the number is not that good as parallelizing stuff. I have seen bigger speed ups for other computers than what I have here and for previous versions of number. So that could look different for your computer. But sort of this is something you could try out if you want to see whether you can speed up the things that you are doing. Finally, sort of there is a fundamental limitation to parallelization. First of all, some stuff cannot be parallelized. If you have sort of operations where you need the result of the first iteration in a loop for the second iteration, if this is an autoregressive process, for example, then the problems are inherently sequential, so you cannot do parallelization. So that's sort of that's the limit. And even if it's sort of, let's say you can parallelize 95% of your code, so most of the code can be parallelized. Then even if this code could be put out in infinitely many processes, then you can never get the code to be more than 20 times faster, because it will always be the last 5% which you cannot speed up with parallelization. So sort of parallelization is a really powerful thing, especially if you have very big clusters of computers, supercomputers. But Amdahl's law, as this is called, is sort of a limitation. Thank you. That was all.